Hello students! Welcome to Math&Magic. For today's video, we will talk about joint variation. As mentioned in the previous lesson, variation describes the relationship between two or more quantities known as variables. The dependent variable may increase when the independent variable increases. This variation is known as a direct variation. Meanwhile, the dependent variable may increase when the independent variable decreases. This variation is in inverse form. Now, in real life, dependent quantity or variable is not only affected by a single independent quantity. More often than not, this is influenced by two or more independent quantities or variables. Say for example, the formula for the area of a triangle. It is given by A equals 1/2 times the base times the height of the triangle. Here 1/2 serves as the constant of variation, and the base and the height are two independent variables, which significantly affect the area of our triangle. Likewise, if the base of the triangle is unchanged and the triangle's altitude is doubled, its area is also doubled. In this case, a joint variation exists. Now, joint variation occurs when one quantity varies directly as the product of two or more other quantities. Its equation is given by y equals kxz and read as y varies jointly as x and z, where y is the dependent variable, k is the constant of variation, and both x and z are independent variables. Moreover, by algebraic manipulation, the constant of variation k is equal to the ratio of y and the product of the independent variables x and z. By the way, we cannot graph this type of variation in xy or Cartesian plane. Now, for better understanding, here is our first example. The area of a rhombus, denoted by variable a, varies jointly as the length of the diagonals d sub 1 and d sub 2. A rhombus has an area of 24 square meters when its diagonals are equal to 6 meters and 8 meters. Determine the following. Letter A, constant of variation. Letter B, variation equation. And letter C, area of a rhombus whose diagonals are 5 meters and 12 meters. In this example, we will solve first the value of the constant k. Here we will use the formula a over d sub 1 times d sub 2. This is based on the formula earlier that the constant is the ratio of the dependent and the product of the two independent variables. Substituting the values, it will be k equals 24 over 6 times 8. 6 times 8 is 48. Simplifying 24 over 48, that is equal to 1/2. Thus, the constant of variation is 1/2. For letter B, the variation equation, we will substitute the constant 1/2 to k. In the variation equation, a equals k times d sub 1 times d sub 2. Hence, the variation equation will be a equals 1/2 times d sub 1 times d sub 2. Notice that this equation is the formula for the area of a rhombus. Lastly, determine the area of the rhombus if the diagonals measures 5 meters and 12 meters. For this question, we will use the variation equation in letter B. That is a equals 1/2 d sub 1 times d sub 2. Substituting the measurement of the diagonals, 5 meters and 12 meters. 5 times 12 is 60. 60 times 1/2, the product is 30. Thus, the area of the rhombus is 30 square meters. For our second example, in physics, The kinetic energy of an object varies jointly with its mass and the square of its velocity. If a 64-kilogram person walks at a speed of 0.5 meter per second, then his kinetic energy is 8 joules. If another person runs at 1.5 meters per second and his kinetic energy is 78.75 joules, what is his mass? For this example, we first construct the variation equation. Here we will denote kinetic energy as variable E, mass as variable M, and the velocity as variable V. When written as an equation, it is E equals kmv squared. Solving for the constant k, by algebraic manipulation, k will be equal to E, our dependent variable, over mv squared, or the two independent variables. Substituting the values, k will be equal to 8 over 64 times the square of 0.5. The square of 0.5 is 0.25. 64 times 0.25, the product is 16. Now 8 divided by 16, when simplified, the constant k is equal to 1/2. Substituting this to the equation, it will be E equals 1/2 mv squared. From here, we will use the variation equation to solve the mass of the running man. Using the second set of values, it will be 78.75 equals 1/2 m times the square of 1.5. The square of 1.5 is 2.25. Multiplying both sides by 2 to make 1/2 equal to 1, it will be 157.5 equals 2.25 m. Now dividing both sides by 2.25 to solve for m will be equal to 70. Therefore, the running man has a mass of 70 kilograms. Thank you for watching. God bless.